Keynote lecture, Advances in Whole Graph Embedding, Technologies, Applications, and Performance Evaluation. Maria, you are cordially welcome to start.
So, thank you, Professor Semenkin. Thank you, Professor Stanimirovic, for this kind invitation. I really hope that at some point I will be able to visit such a beautiful part of Russia. I have never been farther than Yekaterinburg, so I don't really know that part of Russia, and I wish I will be there. So today we will talk about whole graph embedding, and somehow I will talk about networks. So because networks are very important, represent a very important way to represent and model interactions and dependencies among variables and observations. So graph embedding actually involves the projection of one network or a set of networks into a vector space. And this embedding, this projection, should retain some structural properties of those networks. So networks are actually the statistical units, the observations that we want to embed in a vector space for further analysis. And there are many different techniques to achieve such embeddings, like graph kernels, matrix factorization, and some other deep learning architectures. And today I will try to focus a little bit on some of those. There are so many that it's impossible to completely review the field, but still I would like to give you a flavor of what is there and what are possible future directions and the possibility for research. I have seen that there are several talks in this conference that are somehow related to those topics. So first of all, let me start with an example. Let's say that we have a network in which there are some nodes and some edges. And suppose that some of the nodes have labels. For example, there are violet. For example, there are violet nodes or orange nodes, and there are some nodes for which the color is not known. So what we would like to do is to provide an embedding, a representation of this network so that we can compute, we can infer the missing label. This type of application finds this type of problem find application in many different fields. For example, in bioinformatics and in computational biology, it is very interesting to assess the function of some proteins. Proteins in human body are many, around 100,000 proteins take part to processes in every cell of our body. For many of them, we know what is the function. For others, we don't know, and we want to infer their function starting from the one of for the proteins for which this is known. Another type of problem is the link prediction. So we have a network, again, in which there are some nodes and some edges connecting the nodes. And what we want to do is to try to predict the appearance of a link. So we want to predict if some new links will show up inside the network. This has many different applications. Since I am Italian, I will provide an example on mafia meetings. This is a paper that was published some years ago, in which somehow they were trying to understand how to model the interactions between two mafia families. One was Mistretta and the other was Bataresi family. So there are some people that are bosses, so they are the major people in the organization. In this case, they are yellow and red nodes, and there are some other nodes that are white that represents other subjects, other persons that are close or useful to the organization. And what we would like to infer is to understand if those people will connect with some of the main people in this organization. Of course, this type of there are so many applications that we can think of, and somehow this the analysis that we do is somehow related to machine learning. So in a supervised machine learning life cycle, what we have is are some raw data. Then we try to structure using some engineering process the data, and from this, once that we have the data in a format that is useful for our algorithms, then we try to learn something about this data, and we build a model. So we have a phase between the raw data and the structured data that is usually called feature engineering, and there is a final part, a downstream analysis, in which we have the prediction tasks. The one that I was mentioning before are node classification or edge predictions, just to name two. When we talk about graphs, when we talk about networks, what actually happens is that we do not engineer features anymore, but actually we automatically learn the features that we will use to model our problem. So in this part, when we try to understand, when we build the features, there is this actually this embedding. So we start from a network for which there are some nodes connected to some others, and for each node we want and we want to associate a vector in some space, the dimensional space RD. We want to associate a vector to each node. So each node in the network will have an associated the vector, and we will get a representation, a vector representation of the whole network. Once that we have this vector representation, we can of course do our downstream analysis. So why is this hard? With respect to what we usually do on, for example, on images or on text or on audio. Actually, all the modern deep learning toolboxes are designed for sequences or grids. So the problem is very well structured. We have a grid, and we apply to this some multi-layer architectures. And this is the same when we talk about recursive neural networks or word-to-vec neural architectures and so forth. And in all those cases, we have a very predetermined structure, topological structure, and we can go over this. And it is also the reason why we are so successful in applying, for example, graphical processing units. You know, the computation is very well structured, and therefore it goes very fast on those modern computing architectures. The thing is that when we go on a network, on a graph, there is no ordering or reference point. This is usually called the isomorphism problem. So the fact that we try to recognize if two networks, if two graphs are the same or not. And what happens is that it might also be a dynamic situation, a temporal graph, and it also can be that we have for each node of the graph, we have some multimodal features. So a vector of features that is connected to each node and describes such node. So in traditional approaches to machine learning using graphs, what we do, we use a standard machine learning paradigm, a standard machine learning paradigm. What does it mean? Actually, what we do, we extract some statistics from the network, and we use these statistics to represent our network. So each network is represented by a set of statistics, so a vector of statistics, and then using this representation, we can do some downstream analysis like clustering or outlier detection or whatever we want to achieve, regression or whatever. Now, what are those statistics? For example, we might use the node degree. So we could count the number of edges that are connected to a node, or we could use some form of centrality, like between centrality, eigenvector centrality, or other forms of centralities. Or we could introduce some clustering coefficient that somehow represents. What are the limits of those representations? The thing is that very different networks, even having a different number of nodes, might end up in having the same vector representation. So the clustering coefficient or the node statistic, the node edge statistics might be the same for very different networks, and therefore it becomes impossible to discriminate between two of those networks. So the effect of this operation, nevertheless, is the fact that we encode nodes as low-dimensional vectors. And now we want to try to introduce some other techniques to do these node embeddings. So the aim is to project the nodes of the network in some latent space in which we maintain the relationships, the geometric relations that exist among the nodes. So we start with an original network, we do the encoding, for example, of node U and node V, and we obtain some vector representation ZU and ZV. There are several ways to do so, but in general, what we try to do is to structure this process using two main steps. One is called the encoding model, and the other is called the decoder model. So once that we have a node, we encode this node using this vector, and in this encoding phase, and in the decoding phase, what we try to do is to recognize, to reconstruct the information that we have been using to build such network representation. For example, we might try to recover the neighborhoods of the node in itself in this decoding phase. So the encoder, as we said, maps the nodes of the network into an embedding vector. The nodes, sorry, of the network into an embedding vector in some dimensional space D. And the encoding is therefore a function that starts from the set of nodes and arrives to this d-dimensional vector space. In general, we call this type of embedding shallow embedding, in the sense that this encoder is a very simple function, and usually to obtain the representation, what we do, we just do a lookup based on the node identification. So we will have a matrix in which each row represents a node, and the columns represents the d variables in which of the space in which we are the d dimensions of the space in which we are representing our network. So this is shallow in the sense that there is no exchange of parameters or whatsoever to obtain this type of embedding. And the most simple and also the most used encoders and decoders are those that are pairwise. So the decoder usually is a function that takes the two representations of the two nodes and produces some kind of number, some kind of similarity. So those pairwise decoders that can therefore be interpreted as predicting the relationship or the similarity that exists between each pair of nodes. As I said, the decoding phase is somehow devoted to reconstruct what is happening in the original network. So we need to define those two steps, decoder and encoders in order to obtain our embedding. So in general, the goal of this optimizing, the goal is to optimizing the encoder and the decoder to minimize some reconstruction loss. So what we want is that the encoding of two of those nodes is that we will denote as the code of ZV. These are the vector representation of the embedding vector representation is approximately similar to some similarity measure. So in the easiest, most simple case, we can use for similarity as a similarity measure actually the adjacency matrix. That is the matrix that encodes the fact that two nodes are either connected by some link or not. And as I said, so the adjacency matrix has as many rows as the number of nodes, as many columns as the number of columns, and has a 1 in position ij if node I is connected with node j in the network. So what does it mean to optimize this, to minimize this loss? Somehow, in practice, what we do, we minimize an empirical reconstruction loss, which is over a set of some nodes, of some training node pairs. So we take a training set, and starting from this, we try to minimize the empirical reconstruction loss. So the loss measures the difference between what we decode, the decoder provides, and what is this similarity measure that we decided to target. So this loss function is therefore measuring the discrepancy that exists between what we have been estimating using the decoder function and the true values of this similarity matrix. And depending on the definition of the decoding and S and the loss function, we obtain many different algorithms. So, for example, many different methods. For example, if the decoder measures the distance using the L2 norm, and we use a general measure and the loss function that is based on the similarity between U and V, we end up in what is called the Laplacian eigenmaps. And the other algorithms like graph factorization, graph replication, HOPE, deep walk, node2vec, that are somehow quite famous in this field, they can all be recovered using this type of reasoning. So each algorithm has a different decoder, a different similarity measures, and a different loss function. Those are the ingredients to get a novel method. Some of those are intrinsically deterministic, some other introduce some form of stochasticity using some definition of conditional probability. So in this shallow embedding realm, actually what happens is that the representation that we get for each node somehow does not share in the process of obtaining this representation. Somehow we do not share any parameters between the nodes in the encoder, because, as we said, the encoder directly optimizes one embedding vector for each node, going to minimize the empirical loss function. And this, from a statistical perspective, of course, is quite inefficient, because we are not trying to share some parameters that can improve the efficiency of the learning process. From a computational perspective, the number of parameters grows linearly with the number of nodes. And somehow this might become intractable in case of a very massive graph. Nowadays, we can talk easily about networks that represent some physical or some technological problem that have millions of nodes and millions, tens of millions of edges. So what we are trying, and another limitation of those methods is the fact that those type of embeddings actually do not use any information related to the nodes. So if we have some information on the node, and we call this a node feature, this information is not used in the encoder. So another class of methods that actually in somehow overcome those limits are called graph neural networks. And what we want to now to show is how, in a very light way, how we can introduce this formalism, this graph neural network formalism for defining deep neural networks on networks data. In this talk, I'm using interchangeably the word graph and the word network. In some cases, in some disciplines, this is often the case. So the two words represent exactly the same object. In some other cases, there are some differences, but for what I'm talking about today, somehow I can use the word graph and word network as synonymous. So the key idea is to generate some representation in graph neural networks. The key idea is to generate some representation of the nodes that depend on the structure of the graph. So we want to take into account the structure of the graph and the features that are available in order to obtain the embedding representation. So what we might imagine is just to do as we do for images. So we take now we take the matrix that represents the graph, the adjacency matrix that I was describing before. We could take it one row at a time, and then we could feed this to a multi-layer perceptron. And in this case, we would obtain a network representation. Here, this symbol represents the concatenation, the vector concatenation. So this is the first thing that we could do. The thing is that if we change the order of the labeling of the nodes, the order in which we take those nodes, then the vector representation will change. And this is something that we don't like. We would like to have something that somehow preserves the characteristics of the network independently of the node labeling. There are two variants. So what we can do is either use some functions that somehow are permutation invariants. So if we apply a permutation to the adjacency matrix, this does not alter the result of the embedding, or we can use some permutation equivariance, which means that each permutation of the adjacency matrix is therefore visible when we have obtained the representation of our embedding. So we will see that somehow we know that the shallow encoders that we have seen so far, the one that I was describing before optimizing the empirical loss function, are equivariant function. Now, what we want to do is to ensure the invariance of equivariance of those function f, of those embedding f, in the moment in which we apply this to these two graphs. This is very important for a reason, because if we have two networks that are exactly the same, but they have a different node labeling, we don't want them to be embedded in different ways. We want exactly the same embedding for networks that are the same, but have a different node labeling, node ordering. So, to define graph neural network, what we use is a form of a neural message passing. So we have a vector, we have some vector messages that are exchanged between the nodes, and these are used to update our neural network. And we will actually focus on this message passing network, and in this phase, we start with an input graph that is composed by its node and its edges, and a set of features for each node. So we have a vector of, we have a matrix of node features, and we want to use this information to generate the embedding, this final vector that will represent each node in the this final vector that will represent each node in the network. So in this message passing, what happens is that we produce iteratively a representation of this embedding. So we have what we call HUK, that is the representation at step K, the vector representation of step at step K of node U. And this is updated at each step, let's call it step, this is an iterative process, and using this aggregation. So at each step, we aggregate the information coming, we start aggregating the information coming, for example, from neighborhood nodes, and at the next step, we use the information that is provided by the nodes that are neighborhood of those nodes that have been aggregated before to update this hidden embedding representation. So we can now express this process using two functions. One is the update function, and the other is the aggregate function. So in the aggregate step, what we do, we use the information that come from a neighborhood, from the nodes that are neighborhood of the node U, to update this, to obtain, we aggregate the information coming from the node V to the actual vector representation that we have, the embedding representation that we have at step K. And in the update method, we update this representation of node U to obtain the representation at step K plus 1. So each node uses the information of the nodes that are somehow around him in this network, and to obtain an updated representation. So what we can write this as an update. So the representation at step K plus 1 of the vector of the embedding vector of node U is obtained with an update function that takes the previous representation and uses this message coming from the neighborhood of the node to update update actually this representation. So update and aggregate are arbitrary differentiable function, and this is why it would be better to call those objects differentiable objects rather than neural networks. I don't see many neurons in all this, but still we keep with the historical way to represent those objects, and we will continue to use this notation, let's say, and this way of calling those definitions for those objects. So M is the message that is, as I said, that is obtained by the aggregation of the nodes. So, for example, at some point, this function M might, for example, be if each node has one feature, we might take all the neighbors nodes of the node V of the node U, and we can, for example, use the average of this feature value as a message to update the node representation. And we explore little by little the network, because as we said, at each step we obtain a view slightly larger of what is happening around a fixed node, a fixed node U. We cannot go very, very far. So in our exploration, we cannot go very, very far because what happens is that we end up in this phenomena that is called oversmoothing. So if we extend our exploration and we extend this message passing machinery too much, so if we aggregate from too far, we end up with a representation of each node that is exactly the same. The vector representing each node does not differ much from the vector representing another node, and therefore all downstream analyses are impossible. So, as we said, unlikely the shallow embedding methods, the graph neural networks require node features as input models. But in many applications, these are not available, and so there are techniques to just try to obtain these features, like hot encoding. We can provide some numbering of the nodes and then transform this in a vector with an hot encoding. So, so far we have seen those graph neural network, as we said, as an update and aggregate function, but we can also rewrite those in terms of matrix operation, which of course is more useful in the case that we use some specific hardware for the computation. On one side, of course, this helps because if we have a tensor structured computation, we know that we can go pretty fast on GPUs. On the other end, graphs are usually sparse, so not every node is connected with every other node. This means the adjacency matrix, the one that encodes the connection between node I and J, is somehow sparse matrix in which the number of ones is very low, is very limited, and therefore we need to understand where we are, what is the problem that we have at hand, in order to in order to understand if this notation is better or is useful or not. In this type of architectures, we can implement many different things. We can implement attention mechanisms as in standard transformers. We can implement multi-head architectures in order to obtain different methods. And this is exactly what, for methods like G80, the graph attention networks, the attention mechanism is somehow a weighting of the neighborhood nodes in order to retain all information that is important from only some nodes, not all the nodes that are around me. So in this message step that I was describing, we do not take in consideration all the nodes in the same way, but rather we weight them. And we can also use multi-head attention. In this case, we have not only one. We do not only have one weight for each neighbor, but rather we have a tensor of weights. So far, we have been talking about one network, but what happens if we have multiple networks and we want to embed those networks in a vector space? So in this case, now we have a set of networks, a set of graphs, and we want to obtain one vector for each of those graphs. So we want to embed each graph in a space, in an RD space, in a d-dimensional space. This, of course, is very useful. So to each now, in this case, to each graph corresponds to one network. Whereas before, to each node of a network, we were associating one vector. So this is very useful because once that we embed a family, suppose that we have multiple networks belonging to different classes, we can obtain a vector representation and we can use standard, as we said, downstream data analytics techniques in order to do graph classification, graph clustering, and so forth. I will only go very fast in one of those applications. There are many applications of this bull graph embedding, this situation in which we take sets of graph and we embed in a vector space. And this is, for example, related to, this is one of the first study for neurodegenerative diseases. This is something that is very well cited because it gave start to a very rich research field. So what people do, they take magnetic resonance data. These data are stacks of slices of the brain, and they segment those images using some atlases. There are many different atlases. In this case, the atlas had only 66 subregions. The more modern ones are much richer, so we have a much fine-grained representation of our brain and the function of this brain. On the other hand, what we take the diffusion spectrum, so the signals that are coming, that can be acquired by the intensity levels that we find in the colors of those images, in the gray levels of those images. So we take this signal, and what we try to do, we try to understand if there is a correlation between the signal coming from one part of the brain and the signal coming from another part. In case there is a correlation, then what we do, we connect the two parts of the brain. So each edge, each node here is a brain, an anatomical subregion of the brain. Each node is this, and each edge is the fact that there is that a signal is triggered in one part, the same signal, another signal is triggered in another part. Then we take, let's say, 100 patients that are normal, we take 100 Alzheimer patients, and we try to classify, we embed, we build the network, we embed the network, and we try to understand how we can, for example, do a supervised classification. So in the case a new patient arrives, we want to understand if he is an Alzheimer patient or he is a control person. So the approaches to bull graph embedding are so many. As we have seen, we have the same names that we have seen before in the single graph embedding. There are some of those that we have analyzed, that we have been mentioning. And I would like, in the last very few minutes that I have, I think about 4 minutes, I would like to explain how we can use those methods to obtain somehow some interesting representation of network. So we started, the story starts on graph around 2014. So 10 years ago, there was the first paper in which there was this, actually in 2017, because in 2014, it was the year in which Doc2Vec was presented at ICML. What is Doc2Vec? This is a network architectures and neural architectures that takes some documents and provide a representation and embedding of this set of documents. And this can be used for, of course, for classification. And using this idea of Doc2Vec, in 2017, Narayan and others provided the Graph2Vec. So the first algorithm, among the first algorithms that were taking the graph and they were using this idea of the skipgram to obtain a representation of the network. So in this case, the representation of each node in the graph was obtained was a word. So each node in each graph was represented by word. This word was obtained concatenating the node labels of the nodes that were in a neighborhood. So in the same way as I was explaining in the graph neural network architectures, little by little, they were expanding this search around the node and obtaining the nodes that are in the neighborhood, and concatenating this, they were obtaining a word. They were feeding all those words coming from all the nodes in the network to the Doc2Vec. And this was providing a vector representation, and therefore it was possible to do the representation. So what we decided to do back in 2021 was to use a different approach to represent those nodes. So Suppose that you have a node N1. This is a weighted graph, but it is the same if for unweighted graph. So we have a number that is connected to each edge. So suppose that you have the node 1. Let's start from this representation. This is the node distance distribution. This node distance distribution counts the fraction of the nodes that are at distance 1, at distance 2, so that I can reach in one step or in 1, 2 steps, starting from a fixed node. Of course, this we have to do this on weighting this and binding those distances. So what we obtain the fraction of nodes that are at distance 1, 2 diameter from each node. And we obtain this for every node in the graph. We can now order those numbers and we can take the labels. So we can say that, for example, in the node distance distribution of node 1, we have labels 1, 2, 4, 1, 5, obtaining starting from the ordering of those bins. So these are words. We can take those words and we can feed this doc2vec. So we have a string representation of the graph. And this works pretty well. You can use very different empirical probability distribution. You can use transition metrics, but you can invent whatever you like. You build up this representation and you feed the doc2vec, and this works, as I said, incredibly well. This paper contains, there are the examples in this paper that we published, and we also provide the code and the network example to replicate our studies. We used a software that generates graph, which generated 1,600 graphs having a different structures. A set of graphs were very tiny, connected, whereas the other set of graphs had a certain number of communities inside. And we wanted to see if this machinery that we set it up was able to discriminate those two conditions. These are the representations. So what we get here is, so each point is one graph, and this is the t-SNE representation of the embedding of the networks. On the embedding, we did a supervised classifications, and those are the values for the accuracy for tenfold cross-validation of those results. So as we can see, there are cases in which this machinery is very, very effective. So I would like to stop here since my time is over, and you can download this set of slides using this QR code. I am always available if you need, if you can contact me, and thank you for the opportunity to talk in this conference.
Thank you very much for your interesting presentation. Very informative. Dear colleagues, any questions? Who would like to ask question and get answer?
Hello, I have one question.
Yeah, you're welcome.
Well, actually, it's not a question about your talk, but maybe a suggestion or a point for discussion. You have mentioned neural networks with attention. Recently, I have read about neural networks, which not artificial, natural neural networks, which also have such areas in our brain, which corresponds to different points in a space. That means our brain help us to define different objects in space. When I look on your graph structure, I also try to think about some topology, about different nodes in different places. Maybe it will be a good idea to use not embedding, because embedding try to find some, how to say, some dense parts in space, in a spare space. So maybe some techniques about topology will be more efficient for such kind of tasks. Thank you.
So thank you for the interesting question. It's something to which I have never thought, but I think that in this moment we really need to to do more research in this field, because those techniques work. In some cases, they are very effective, but in some other cases, they completely fail. So I really think that there are many opportunities for research. So somehow I had a slide. I'm sorry because I didn't show this because the limited time, but as I said, if you use the QR code, you can download the complete set of slides, or you can ask me in case you need. Just search Mario Guarracino on Yandex or Google, and you will find my email. It's not a big deal. And so somehow what you were mentioning is somehow related to the expressiveness of those representations, because somehow what we have so far, and actually this was a very good point in your question, we have a representation that is devoted to the fact. So what we try to do is to understand if two graphs are the same or not. So now, at the base of all the reasonings that we did on those algorithms, somehow there is the idea that we should be able to understand if two graphs are isomorphic or not. Now, in reality, this is not the only question that we want. We want to, for example, I was mentioning how do you say, the Alzheimer disease. So we want to do a diagnosis to understand what subtype of Alzheimer one patient has. We don't want to see if this patient is exactly equal to another patient. We want to see how close it is. So I think that there is a full kind of applications in which those methods somehow fail, and that can be improved. So any ideas is good. The thing is that we need to be very careful about the computational complexity of the proposed methods, because some are very slow. So if you start thinking about computing distances of those objects using, for example, before I was talking about empirical probability distribution representation of the network. In that case, you could use some distance, some probability distribution distance, but this is quite inefficient. So everything should be investigated, is very good to be investigated, but in the light of the fact that this should then be implemented. So we should then compute something in a time that is, of course, should be useful for our, for example, diagnosis. We cannot provide the diagnosis when the patient is already dead, or the diagnosis is not useful anymore. I hope that this at least partially answered your question.
Yeah, thank you very much, and thank you again for your presentation.
Alex, any other question? I have a small question. I did not catch from presentation. Is this approach applicable to oriented graph, non-oriented graphs, or mixed graph?
So, okay, this is very good. This is very good question. So when we use in this approach that I was proposing, in this example, we have transition matrix. A transition matrix is a matrix that encodes the probability of a random walker starting from one node to reach in another node in a fixed number of steps. Of course, this can be extended in the case of directed graphs. And for the node distance distribution, for example, we might look at outgoing edges. So for directed graph, the answer is yes. For weighted, yes. For multigraph, in some cases, but still, for example, this technique is the technique that I am talking now is not able to take full advantage of the node labels. So this also would require some reasoning. So if you have some characteristic of the nodes that you want to use in the embedding. In this case, we are only looking at the wiring and at the topology of the network rather than to the characteristics of the single nodes. So yes, this method can be extended, but we didn't do this so far.
Okay, thank you very much. Well, ladies and gentlemen, now we have 10 minutes for the rest, 12 minutes until the next keynote lecture, and you are free to drink your water or something like that.
Thank you again